Hello math lovers, welcome to the channel. In this video I have brought a very interesting geometry question for you. The question is, what is the area of a circle inscribed in a semicircle which in turn is inscribed in a quarter circle as shown in the diagram? The radius of the quarter circle is 3 units. You can see that there is a quarter circle. So the radius of this quarter circle is 3 units. Then in this quarter circle we can see that a semicircle is inscribed in it, and inside the semicircle there is a circle inscribed in it. So we need to find out the area of this full circle. So let's find out, but we need some constructions in order to find out the area of the circle. So let's prepare the constructions and then I'll explain you how to solve this interesting question. So friends, we have done with our construction, so let me explain them to you step by step. So friends, we have joined the center of this quarter circle O to a point on this chord AB at C. So this line OC is perpendicular to this chord AB. So this line OC bisects this chord AB. This is because in a circle, if a line that passes through the center is perpendicular to any of its chord, then that line bisects the chord. So here we can say that AC is equal to BC. Again, we see that AB, which is a chord to the quarter circle, is a diameter to this semicircle. So AC and BC are the radii of this semicircle. Similarly, CN and CD are also the radii of this semicircle. CN is perpendicular to PO. That is because CN passes through the center of the semicircle and touches this tangent PO. So any radius that touches the point of contact of a tangent is perpendicular to the tangent. Similarly, CD is also perpendicular to tangent QO. Finally, we extend this line OC until it reaches the circumference of this quarter circle at M. So we get CM. We have now done with our construction. So let's find out the area of this full circle. So now I am going to explain you the steps one by one in finding out the area of this full circle. So let's do it. The quadrilateral NCDO is a square. So why we say that NCDO is a square? And this is because the adjacent sides of this quadrilateral CN and CD are of equal length. They are the radius of this semicircle. So they are equal in length. So let's denote their lengths by a small letter R. Then we see that CD is perpendicular to QO, and PO, which contains the opposite side, is also perpendicular to QO, which means that CD is parallel to NO. Similarly, CN is perpendicular to PO and QO is also perpendicular to PO. So side CN is parallel to DO. If in any quadrilateral, if the opposite sides are parallel and two adjacent sides are equal in length, then the quadrilateral is definitely a square. So NCDO is a square. Now friends, I want you to focus on the right angle triangle NCO. So in this right angle triangle we need to find out the length of CO. So we can use the Pythagoras theorem. So in Pythagoras theorem, a square plus b square equals to c square, where c square is the hypotenuse. So here also we have NO square plus NC square will be equal to CO square. So we have NO equal to R. This is because all the sides of the square are equal. So if CD and CN have the length equal to R, so NO and DO is also equal to R. According to the Pythagoras theorem, we have R square plus R square will be CO square. So CO will be equal to root 2 times R. Now we'll move on to the next step. So moving on to the next step, I want you to recall the intersecting chords theorem. So this intersecting chords theorem says that when two chords of a circle intersect within the circle, the product of the segments of one chord is equal to the product of the segments of the other chord. So when you look at this quarter circle, you can find out that there are two chords. One is AB and the another is MX. These two chords intersect at C. So our segments are AC and BC, whereas another two segments are MC and CX. So now you may be willing to ask me a question that you are able to see C but you are not able to see X. So for that you have to imagine a full circle for this quarter circle. So if you imagine a full circle for this quarter circle, and then if you extend this radius MO to the point on the circumference on the opposite side, so the point at which this radius MO meets the circumference, that point is X. So OX is also the radius of this quarter circle, and OX is equal to 3. So executing this theorem, we have AC equal to R and BC also equal to R. So the product of R into R is R square, and that will be equal to the product of MC times CX. So we have MC equal to OM minus OC. So we have OM equal to 3 units, whereas OC is equal to root 2 times R, which we have just found out. So MC is 3 minus root 2 times R. Then we'll move to another segment, that is CX. So CX is the sum of CO and OX, where OX is equal to 3 units, whereas CO is equal to root 2 times R. So we have Cx equal to 3 plus root 2r. So r square is equal to 3 minus root 2r times 3 plus root 2r. Now I want you to recall the famous identity, that is a minus b, a plus b equals to a square minus b square. So 3 will become 9 and root 2r will become 2r square. So after we simplify this, we'll get that r equals to root 3. So we now know that the radius of this semicircle is root 3, but cy is also the radius of this semicircle. That means cy is root 3, but we see that cy is the diameter of this full circle. So the diameter of this full circle is root 3. So that means that the radius of this full circle will be root 3 over 2. We need the area of this circle. So area of any circle is pi r square. So pi, if we take it as 22 over 7, r will be root 3 over 2. So we'll square that, and finally when we will solve this, we'll get area of this full circle as approximately equal to 2.35 square units. Therefore the area of the circle in question is 2.35 square units approx. Thank you, and if you like my explanation, then you can press that like button, and please do not forget to subscribe the channel, because I will be bringing more such useful videos in the times to come. Thank you.